Welcome to this video on inference. This is chapter 4 in Wooldridge's book, following on multiple regression analysis, and we're also going to discuss this here in the context of multiple regression. This is what we're going to cover. We're going to talk about the sampling distributions of the OLS estimators. We're going to talk about testing hypotheses about a single population parameter. So that will be the Ttest. We're going to talk about confidence intervals. And finally, we're going to talk about testing multiple linear restrictions. And that's going to be the Ftest. So let's start with the sampling distributions of the OLS estimators. First of all, why do we care? We do care because we want to be able to tell how certain we are about our estimates of the parameters. And this is essentially what inference is all about. And we're going to see this in the following, what exactly I mean by that. So let me first go back to the assumptions that we have already made for multiple linear regression. So we had 5 assumptions: linearity in parameters, random sampling, no perfect collinearity, the zero conditional mean assumption, which is really important because this assumption makes sure that we're shooting at the right target, let's say, so that our estimators estimate the right thing. And this is something I'm not going to talk about here. I'm just highlighting it. We'll come back to that later. And homoscedasticity. So homoscedasticity is already going a little bit in the direction in which I'm going to go in this video today. Homoscedasticity means that the variance of the variance of the error term, the U, I have to be very careful here, the variance of the error term in our linear regression model does not depend on any of the x's, and that variance is always going to be equal to sigma square. What I'm adding now in this chapter here, or in this presentation here, is assumption number 6, and that is normality. So normality here means normality of the population error term, U, and we're going to assume that the U is normally distributed, and I already know what the variance is going to be. It's going to be that sigma square from the homoscedasticity assumption, and the mean is going to be 0. So we talked about this also earlier as a relatively innocuous normalization. So it's not completely surprising that I have a mean of 0 here. Now, we're going to have independence of the explanatory variables x. So what we'll have is that really this is sigma square and that this u is independent of x. What does that mean in terms of a picture? In terms of a picture, it means that we can think of the data in the following way. So I have an x-axis here in this plot, and I have a y. Okay, so that's a 2-dimensional plot when I just look at this part here. So I'm plotting here beta naught plus beta 1 x, let's say. Here you see it. So this is the expectation of y given x. And what I have now here on this third axis is the density of y given x. So under the assumptions on the previous slide, what I'll have is that I have a normal distribution for the y given that x, and I have a normal distribution here, I have a normal distribution here, and I have a normal distribution here, and they're all the same normal distribution because for a given x, the distribution in the y only comes from the error term u, and we have assumed that that distribution does not depend on x. So therefore, I get 3 times the same distribution here, and again this is the density of y given x, which will be basically a shifted version of the density of u that we've assumed. And the density of u is the density of a normal distribution with variance sigma square. Now, whether normality holds is ultimately something we can test, right? I'm not going to tell you here how we're going to test that or whether we're going to test that, but in principle you can test that because we can always make the thought experiment of having many observations. Then we're going to be able to estimate our parameters very precisely, and then we can look at the residuals, and the residuals are going to be very similar to the error terms in the econometric model because our betas are going to be estimated very precisely. So essentially, when we have a lot of observations, we observe the error term, and then we can just test using a standard test whether they're normally distributed. That's not the point of this whole presentation here. I just want to mention it. At the same time, I also want to mention that sometimes normality really cannot hold, right? If the dependent variable is non-negative, for instance, like a wage or price or something like this, then we can't have certain values of the u, and that means that on theoretical grounds we know that normality cannot hold. Okay. What I want you to do here is to think of this as an assumption that may or may not hold approximately, that we can test whether that's the case, and this is going to be just very helpful for developing all these results. And later in chapter 5, we're actually going to see that it really does not have to hold in our data, so we don't actually have to assume this. This is just a simplification. So everything will also work out fine in large samples, because then we can use actually asymptotics. But this is for later. For now, we're just gonna go with normality, and as I said, this is mainly for simplicity. Now, here I already have like the main result that we're going to use here, and that result is in theorem 4.1 in Wooldridge, and that theorem says that under these 6 assumptions, the 5th being homoscedasticity, the 6th being normality of the error term, what we do have for given x's, so conditional on the independent variables, what we do have is that our estimates beta j hat are going to be normally distributed with mean beta j and variance beta j hat, and there's a formula for that variance, and what that means, conversely, or another way to write that is that beta j hat minus beta j divided by the standard deviation of beta j hat is going to be standard normally distributed. And besides that, it's actually true that the beta j hats have a joint normal distribution, right? So this statement here is about one beta j hat, so that's going to be a normal distribution, and I have many of these beta j hats, so one for the intercept and k slope coefficients in the general version of the model, and then they're going to have a joint normal distribution. That's already concluding the first part of this presentation. With this result in hand, we can think about testing. and what I want to start with here is testing hypotheses about a single parameter, and that's going to be the so-called Ttest, and I will tell you why this is called Ttest. This might ring a bell because it might remind you of some material in statistics that you have seen before. Now, let's start with the objective. So if the objective is that we want to formulate hypotheses about the unknown population parameters, and actually, in fact, one of them, then we can use the Ttest, and we can use statistical inference to test these hypotheses. Okay, so theorem 4.2 follows almost immediately up on theorem 4.1, which established a normality of the betas, and theorem 4.2 says that the standardized estimators are going to have a t-distribution. Okay, so the formal statement is that under these 6 assumptions and conditional on the independent variables, the x's, as we did stated in theorem 4.1, we have that beta j hat minus beta j divided by the standard error of beta j hat will have a t-distribution. Okay, and the t-distribution is indexed by something here, and that is giving us the degrees of freedom that we have to take into account. We'll get to that in a minute. For now, let me just draw the parallel to the earlier result in theorem 4.1. So earlier, we have seen that beta j hat minus beta j divided by the standard deviation of beta j hat has a standard normal distribution. Okay, so the one difference that we have here now is that we have replaced the standard deviation of beta j hat. That, by the way, we normally don't know. This is an unobserved quantity. We have replaced it by an estimator, and that estimator is the so-called standard error. We have seen that before, and we can estimate the standard error simply by estimating the variance of the u using the variance of the residual, and when we do that, then we actually get this result here. So it's a t-distribution. Okay, and where does the n minus k minus 1 come from? Well, that's the degrees of freedom that we have when we estimate the variance of the u's by using an estimator for the variance of the residuals. We're going to have n minus k minus 1 degrees of freedom because we have n observations, and we estimate k slope coefficients and 1 intercept. So therefore it's n minus k minus 1. Good. So let's get back to our objective to test a null hypothesis. So let's think about the null hypothesis that beta j is equal to 0. So for instance, we could have a wage equation that normally has this log wage on the left-hand side and has a linear function of explanatory variables on the right-hand side. So this is a classical way of writing down a wage equation, semi-elasticity, functional form, if this rings a bell. So we might want to test the null hypothesis that beta 2 is equal to 0. So that means that work experience, which is this variable here, xper, does not affect wages once we have education and tenure in the model. Okay, so to test this hypothesis, what we can do is we can calculate the t-statistic. So the t-statistic is going to be our estimate of beta j, and we're going to divide it by the standard error of that estimate, and then we get a number, right? We'll get to that number in a bit, but before that, let us briefly pause and think about why this is actually a good statistic for testing the null hypothesis that beta j is equal to 0 against any alternative. Well, the answer to that question is that it could be that we get a very high estimate in a statistical sense of beta j. Then we will reject the null. Or we get a low estimate of beta j, then we also reject the null. Okay, we can actually, the t-statistic is very useful because we can easily use it to test a null against basically in practice two types of alternative hypotheses. One is that of a two-sided t-test, so it could be either very high or very low as an alternative, or it could be a one-sided version where we say the alternative is that it is, say, greater than 0 because experience has a positive effect on wages. We'll get to that in more detail in a few slides. Good. So let's first think this through for one-sided alternatives. So a one-sided alternative hypothesis, as I said, would be, for instance, that beta j is greater than 0. So what that means is that under the null, the t-statistic, t of beta j hat, is expected to be 0, whereas under the alternative, the t-statistic is expected to be positive. So this means in turn that we reject the null if the t-statistics is above some critical value. And that critical value is called C here. And all this is also called a one-tailed test for that reason. Now, how do we choose that critical value C? Well, we choose it so that the probability of rejecting the null when it is true equals some given significance level. Typical significance level is 5%, so that gives a 5% level test, and for that 5% level, the critical value C equals the 95th percentile of the appropriate t-distribution. And as I said earlier, this might all ring a bell. It's the exact same logic as you've had earlier in statistics. The one difference could be that there you haven't seen it for regressions, but it's the exact same idea. Now, where do I find these quantiles? For instance, in Wooldridge's table G2, but that's very old school, right? Normally, you can simply use statistical software and ask that software for that value. So the t-distribution is basically programmed up. So you can just use a command to get it, so you don't need to really look it up in practice. Another thing that's important, and that is much more important than even in this presentation here, for large degrees of freedom, actually the t-distribution is approximately equal to the standard normal distribution, so you can just use standard normal quantiles, right? So you don't really have to go and look up stuff for the t-distribution when I have like more than 100 degrees of freedom. And in practice, you know, in most applications, you will actually have much more than 100 degrees of freedom. So this is really the relevant case. In practice, today we're going to see some examples with lower numbers, simply to really show you how this works. But then later, this degrees of freedom business is less relevant in practice. Now, So suppose you do all that, you formulate your null, you formulate your alternative, you find your critical value, thereby you conduct your test, right? What this gives you is that you either conclude that you reject the null, or you fail, or you do not reject the null at a given significance level. Okay, we never really say when we do not reject the null that we accept it, and that is important. Okay, so I just want to stress that here. In terms of a picture, this picture is taken from Wooldridge. It's figure 4.2. What it shows is the 5% rejection rule for the alternative that beta j is greater than 0 with 28 degrees of freedom. You have here the t distribution, and from the table you find that the critical value is going to be 1.701, and when your test statistic is above that critical value, you're going to reject the null in favor of the alternative, and this area under the curve is exactly your 5% probability that you reject the null if it is actually true. Right, because this is the distribution of the test statistic under the null and under the null, for this level of significance, we're saying, okay, the likelihood that I reject the null, if it is actually true, is 5%. So therefore, the picture has to look like this. Where do you get these values from? I told you normally you get them from statistical software. Just for illustration, here's the table from Wooldridge's book. So normally what you have here, you have the rows. So this gives you the degrees of freedom. Then you have the significance level. So now we looked at the one-tailed test. So when the significance level is 5%, then you see here your critical value. That gives you the numbers that correspond to your degrees of freedom. And before we had like 28 degrees of freedom, 5% level of significance. So I have to go 28, 5, so 1.701. So this is the number we saw on the previous slide. All right, so that's hopefully clear. Now let's look at another example. So here you have this wage equation that we saw before. That's summarizing the output that you get when you run a regression. Here's your intercept, estimate of the intercept, standard error, estimate of your slope for education, years of education, standard error, work experience, standard error, coefficient on tenure, standard error. So tenure again is the number of years you have been working for the same employer. That should capture something like firm-specific human capital that you've acquired. This is kind of old school data, very few observations. So nowadays we would have many more usually, but just for illustration, that's fine. 526 observations. How many degrees of freedom? Well, 526 minus 1, 2, 3, 4, 522. Let's say we want to test whether the coefficient on experience is equal to 0 against the alternative that it is greater than 0, because we think it's kind of reasonable that experience doesn't have a negative effect on wages. We can calculate the t statistic. So that would be the coefficient on experience divided by the standard error, which is this ratio here. We get a number that is 2.41. And what we now have to do is to compare this to the critical value. So for the number of degrees of freedom, 522, the t-distribution is virtually identical to the standard normal distribution. So we can just look up the standard normal critical value. We want to have 5% or 1% significance here in this example down here. If we do that, we have to look up the 99th percentile of that distribution, of the standard normal distribution, that is 2.326. 2.326 is smaller than 2.41. So what that means is that we reject the null at a 1% significance level even. Okay. Now, before I move on, let's very briefly pause and recall how we would interpret our coefficient estimates here. So here I have the log weight on the left-hand side, and here I have the number of years of education. So a number of 0.092 would mean that any additional year of education, if I now give this, a causal interpretation, it would mean that it will increases wages by 9.2%, because I have the log on the left-hand side. I'm a bit cautious here, and I'm saying if I give this a causal interpretation, because as you know, for this we need mean independence to hold, and you've heard me before saying that I think here it's probably unlikely that this holds. So if this were a research paper, this wouldn't be so good, but we can say for the sake of this example, we just go with this for now. Okay. All right. The non-causal interpretation, as an aside, is that people who have one more year of education, on average, earn 9.2% more than people who have 1 year less of education. So that's a non-causal statement, because it compares apples to oranges, because people who have more education are generally different from people who have less education, also in terms of other characteristics. Good, let's move on. What I've now done so far is to test against an alternative that beta j is bigger than 0, greater than 0. Of course, I can do the exact same thing for an alternative where beta j is less than 0. Then I'm going to reject if my value of my t-stat is less than the critical value. So the critical value here would then be, for instance, for 18 degrees of freedom, 1.734 minus 1.734. So the rejection region would be to the left of that. So whenever I get a t-stat of less than minus 1.734, I would reject the null in favor of the alternative. Now, these were one-sided tests. We can also do two-sided tests, so testing against two-sided alternatives. So the null is the same as before. Beta j is equal to 0. The alternative would then be that beta j is not equal to 0. We're going to reject the null, therefore, if the absolute value of the t-statistic is bigger than c, and that's going to be the two-tailed test. Again, I'm going to choose the critical value c, such that the probability of rejecting the null when it is true equals a given significance level. So for instance, for the 5% level test, the critical value c equals the 97.5th percentile of the appropriate t-distribution. So that gives me the c, and of course the minus c is then already given because it's symmetric, but it would also be equal to the 2.5th percentile of this very same t-distribution. Now, if the null is rejected in favor of such a two-sided alternative at the 5% level. What we do say is that beta j is statistically significant or statistically different from 0 at the 5% level. And notice that here in the slide there's a typo, so it should be beta j instead of xj. If the null is not rejected, as before, we say that xj is statistically insignificant. Actually, I got that wrong in the previous bullet point, so let's get that right. What we actually say is that the effect of xj is statistically significant, and if h naught is not rejected, what we usually say is that the effect of xj is statistically insignificant. So the xj on the slide is actually not a typo. Now, final point, and that's probably the most important one here, and that is that statistical significance, and that is related to the size of the t-statistic, and it's related to how precisely we estimate beta j, should be distinguished from economic significance. Okay, so that is actually the size of parameter estimates. Both are loosely connected to one another, but they're not the same thing, right? xj, the effect of xj can be statistically significant, but at the same time, it could be that it's still small, right? So the economic significance could still be small or 0, right? It could not matter, even though in a statistical sense, the coefficient is different from 0, as we conclude from a test like this. Here's a figure illustrating the two-sided test. So under the null, our test statistic is going to have this distribution. And we want to say, okay, under the null, even though the effect is 0, we want to reject it in 5% of the cases. So we need 2.5% probability mass here, 2.5% probability mass here. With 25 degrees of freedom, what I need to look up is the 97.5th percentile of the t-distribution. That is 2.06. It's symmetric, so the 2.5th percentile is minus 2.06, and then I'm calculating my test statistic. And if it's further away from 0 than 2.06, either here or here, then I'm gonna reject the null. An example here. This is something we have seen before, determinants of college GPA. So college GPA is regressed on high school GPA and the ACT score, and this is an extra variable whether people have skipped class. What I want to do is I want to test the null that beta j is equal to 0 against the alternative that beta j is different from 0. We have 141 observations. We estimate 1, 2, 3, 4 coefficients. So we have 137 degrees of freedom. So what we can do is we can compare the three t-statistics, which are given by the three parameter estimates for the slopes 1, 2, 3, divided by their respective standard errors, which are these numbers here, to standard normal critical values. Why standard normal? Because we have 137 degrees of freedom, so that's already enough to use the standard normal distribution. When you look at this, then 1.96 is the critical value for the 5% level, when we look at this, this is definitely, so high school GPA is significant at any conventional levels, also at the 1% level, and also the one for skipped class is also at any conventional level, and this one here is smaller than 1.96, so we would say that the ACT score is not significant, or the effect of the ACT score is not significant. Now, so far we have talked about the null hypothesis that beta j is equal to 0, but of course we can also use a more general version of that. So we can say the null hypothesis is that beta j is equal to a number aj, right? And then we can again use a one-sided or two-sided alternative for the test. And the one difference is that then we would not use the ratio of the coefficient estimate and the standard error. We would first subtract this value aj, as usual when one does these simple tests, and as usual in statistics. So you might have seen this before. But the idea is exactly the same as before. An example in the book uses the campus crime data. Basically, if you think of the crime rate or the number of crimes committed as a function of enrollment, you could think of it as, linearly increasing, so it's just proportional. Or when there's more enrollment, it sort of explodes. Or there is something like decreasing effects, right? So these are the things you could imagine, and what you might want to test is whether it's proportional, right? So you might want to test whether beta 1 is equal to 1. So that is this more general test. When you run this regression, again, example is from the book, and actually here there's a log specification. So what that means is that this here is the elasticity. Okay, the log of crime is regressed on the log of enrollment. What that means is here that when enrollment increases by 1%, then crime will increase by 1.27%. And now we might be interested in testing whether that 1.27 is actually significantly different from 1. Okay, so the effect of enrollment in terms of this elasticity is significantly different from 1. So the test is for the null that beta 1 is equal to 1 against the alternative that beta 1 is, for instance, bigger than 1. So that would be a one-sided test. We would reject if 1.27 minus 1 divided by a standard error, which is this 0.11, is bigger than the critical value that we need to find. So first of all, let's calculate the test statistics. So that's 2.45. What is the critical value for the t-statistic with 97 minus 2 degrees of freedom? Why 97 minus 2? 97 observations, 2 coefficients, so 95. Then again, if you go to table G2 in the book, you can by hand look up the critical value, and you will find that it is actually 1.66 at the 5% level for this one-sided test. The test statistic is bigger than the critical value, so you would reject the null in favor of this alternative. And here's again the table that you can look up in the PDF version of the slides to find this yourselves. Good. These were the tests that you can do for one parameter. And so far we had a null, we had an alternative, and we basically took a given level of significance and then rejected the null or not. What you can do alternatively is to compute p-values. The p-value for a test is the smallest significance level at which it would reject the null hypothesis. It's a probability, so it lies between 0 and 1. And statistical software usually reports two-sided p-values for the null that beta j is equal to 0 against the alternative that beta j is not equal to 0. Okay, so it will report the probability that this t distribution is bigger than the t distribution is bigger than the actual value that you find, and we have to find the appropriate distribution for this random variable t. Okay. And then again, p-value is the probability of observing a t-statistic, at least as extreme as the one observed in if the null is true. So a low p-value is evidence against the null hypothesis because it says that it's really, really unlikely that you actually get the value that you find under the null. And we're going to reject the null at a given significance level if the p-value is below that level. Okay, so when I'm saying, you know, I wanna choose a significance level of 5%, and I find a p-value of 1.5%, then I should reject the null hypothesis, because the likelihood to find the actual t-value that you have is 1.5%, and that's below the 5% significance level. Figure 4.6 in the book illustrates this. It's about obtaining the p-value against a two-sided alternative when the t-stat is 1.85 and I have 40 degrees of freedom. Okay, so what you then have to do is you have to look up for 40 degrees of freedom the likelihood that I get a t-stat of at least 1.85 or at most minus 1.85, because we're doing a two-sided test here. Okay, so this area is 0.0359, and then I have here 0.0359, so it's 2 times that, which is about 7%. Okay, so at the 5% level, we would actually not reject. Confidence intervals. These are also actually quite useful, and they're all also related, of course, to what we've seen so far. So a 95% confidence interval, for instance, for the population parameter beta j is an interval estimator beta lower bar j, beta upper bar j of beta j, such that across repeated samples, the probability that beta j lies in that interval is 0.95. Okay, you can also have a 90% confidence interval, then this would be 0.9, or 99%, then it would be 0.99. Okay, so recall, and that's important to realize, this beta j is fixed. Okay, so what will vary is these two things across samples. Okay, how do we construct this? Recall what we had in theorem 4.2. In theorem 4.2, we said basically that beta j hat minus beta j divided by the standard error of beta j hat has a t-distribution with n minus k minus 1 degrees of freedom. Okay. Recall also that the t-distribution, you can recall this from the figures, the t-distribution is symmetric around 0. And one way to remember this is that the t-distribution actually goes becomes the standard normal distribution when they have many degrees of freedom, and the standard normal distribution is symmetric. So that's one way of remembering this, the form of the t-distribution. Okay, the symmetry is useful because what it means is that we can put minus c here and c here, as we have actually already done in one of the figures. So we always saw that this was symmetric, right? So we only have to look up one critical value, even for a two-sided test. What you can do is you can calculate beta hat minus beta j divided by the standard error of beta hat here, and then you have c and minus c, and that should be equal to 95%. The probability that this quantity here falls between minus c and c. Okay. Now I have this. I have the degrees of freedom. I know it's a t-distribution, and I know that this is 95%. So what I need to do is I need to look up the 97.5th percentile of that t-distribution. Okay, so that's going to be my c, and then what I do is, here I have a statement using with two inequalities. I can rearrange stuff. So I can actually just write it as this. This is the same as the probability that beta j hat minus c times the standard error of beta j hat is less than beta j, and then again less than beta j hat plus c times the standard error of beta j hat. Okay, so what that means is that the 95% confidence interval for beta j is given by beta j minus c times the standard error of beta j hat on the one hand. So that's the left end of that interval, and then of course the right end is going to be beta j hat plus c times the standard error of beta j hat. So again, why is this useful? It is useful because what I'm getting here is that with a probability equal to 95%, the true parameter beta j will lie in the interval given here. Okay, so that's quite a meaningful interval. How is this related to two-sided tests? A t-test is testing the null that beta j is equal to aj against the alternative that beta j is not equal to aj at a 5% significance level, and rejects the null if and only if aj lies outside the 95% confidence interval for beta j. Okay, so I get this 95% confidence interval, and then I just need to see whether, so if for instance we test against the alternative that beta j is not equal to 0, right? And I just need to check whether 0 lies in the 95% confidence interval, or let's go to this other example with the elasticity equal to 1 with crime on campus. So there we would test against the alternative that beta j is not equal to 1, so we have to check whether 1 lies inside the 95% confidence interval for beta j. Another example is, again from the book, R&D expenditures. What you have here is a regression of R&D expenditures on a constant term, the log of sales, and the profit margin. So again, that coefficient on a log of sales has an elasticity interpretation. So if sales increase by 1%, then R&D expenditures will increase by approximately 1.084%. or exactly 1.084%. This comes from this data set here. We have 32 observations, which is really low. So nowadays we usually have more, but let's go with this for now. Let's think this through. The 97.5th percentile of the T29 distribution is 2.045, so about 2. Okay, why 29? Because I have 32 observations minus 3 coefficients that I'm estimating. Then I construct the confidence interval, the 95% confidence interval for the coefficient on log sales, and that is given by this value here, 1.084 plus minus 2 times the standard error. So 1.084 minus 2.045 times 0.06 and 1.084 plus 2.045 times 0.06. So when I calculate this, then I get this interval here, and what you see is that 1 is in this is contained in the 95% confidence interval. Can do the same thing for the profit margin, and I see that I get this interval here, and the value 0 is contained in this 95% confidence interval. That means that I cannot reject that the null, that the effect of the profit margin, if I now give this again a causal interpretation, which probably I shouldn't, but let's do that for now, that the effect of the profit margin is significantly different from 0. Now, we've seen t-tests and confidence intervals, and you might now ask the question, and that's a good question, should I use a t-test or a confidence interval? So oftentimes statistical insignificance is misinterpreted, and also sometimes it's not so important to conduct a test, right? So when you go more towards an economic interpretation of parameter values, then confidence intervals are actually quite useful. And when interpreting a confidence interval as those values of the true parameter that are consistent with the observed data, then you'll generally draw the right conclusions. One can argue, right? So confidence intervals are actually quite useful, right? So they give you a range, but if you say that, from my data, I can learn that the true parameter is in that range, and then you go on and give this an economic interpretation, then you're on the right way. But of course, what's also true is that if that range is very wide, then you also have to say that you can't really tell because your data are not so informative about this parameter. And last remark related to this, a confidence interval has a certain width, right? If you get more data, then the width is actually going to shrink, right? That's also important to keep in mind. So that's the value of having more data. Final topic I want to cover here is testing multiple linear restrictions, and that's going to be the Ftest. And one way to approach this, and this is also how it's done in the book, is to think of an unrestricted model with k explanatory variables. So that's just our model with an intercept and k axis, and a null hypothesis that q of these beta coefficients are equal to 0. Okay, so that's going to be the restricted model. I'm not having a k axis anymore. I'm having k minus q axis. Okay, and what I want to do is to test the null that all these are equal to 0 against the alternative that this is not true, basically. And it's already not true when, for instance, one of them is not equal to 0. One of these remaining coefficients, one of these q coefficients. But it's also not true if two are not equal to 0, etc., etc. This is what I want to do here. And for this, we can use the F statistic, or sometimes people call this the F ratio. And this is given by this quantity here. First of all, let's let's think this through intuitively. If the null is true, then it should not really matter whether I estimate the restricted model or the unrestricted model. What does it mean that it doesn't matter? Well, it should then be the case that the residual sum of squares is roughly the same for both models, because the null hypothesis is true, and adding these q variables to the model does not really increase the explanatory power of my regression. So for that reason, it's meaningful to compare the residual sum of squares, or sum of squared residuals, as it's written here, for the restricted model to the one of the unrestricted model. And another thing that's of course true is that you can never do better when you have a restricted model than you can do with an unrestricted model. So that's always going to be a positive quantity here. Okay, so we're going to compare essentially these sums of squared residuals to one another, and we do it in a particular way. We calculate this difference, we divide it by the number of restrictions, and we look at this relative to the sum of squared residuals for the unrestricted model divided by the degrees of freedom. And this is ad hoc, let's say. This is just a result, right? I'm not gonna derive this in any way. But it does actually resemble some of the things that you might have seen in your statistics class before. So it's the exact same logic as in statistics, of course. With this F statistic that we can calculate, so we run both regressions and then we calculate this F statistic, we can test the null. And what will we do? We will basically check whether this F statistic is big. It will have a distribution under the null hypothesis. So therefore, what we can do is we can figure out what, for a given level of significance, the critical value is, and then we can just compare the value of the test statistic that we compute, in our case, after running these two regressions, to that critical value. And again, the F statistic is going to be large if the fit of the restricted model is relatively poor. So if I gain a lot of explanatory power when I use the unrestricted model instead. And then what should be the case is that the sum of squared residuals for the restricted model is much bigger than the sum of squared residuals for the unrestricted model. Why do we use this statistic here? Well, because one can actually show that under the assumptions that we have made, the 6 assumptions we had in the very beginning, we can show that under the null, f, this statistic here, has an f distribution, follows an f distribution under the null. Okay, and the f distribution has 2 parameters, and the 2 parameters are the two numbers here. So it's the number of restrictions and the number of degrees of freedom in the model, in the unrestricted model. Now, I'm going to reject the null at, for instance, the 5% level if that f, the value of the statistic that I'm calculating, is bigger than the critical value, and the critical value is the 95th percentile of this f distribution. And these critical values you can actually look up in Wooldridge's table G3. Probably easiest to draw a picture. So this is figure 4.7 from the book. This gives you the 5% critical value and rejection region for an f distribution with 3 and 60 degrees of freedom. You have an area under the curve, so here you have 95%. So when my statistic is in this range here, I'm not going to reject the null, and the rejection region here starts at 2.76. Here is this table from the book that I've mentioned. Here again you have the denominator degrees of freedom, and here you have the numerator degrees of freedom, and this is now a table for the 5% critical values. So for each level of significance, you get a different table. Notice also that there's no distinction between one-sided and two-sided. So in a way, this is always two-sided, right? This you can see from the way I've actually set this up. I've set the restricted model basically just puts some of the coefficients to particular values, right? And the unrestricted model frees them up. We can also compute p-values for the Ftest. Recall that the p-value for Ttest is, in general, the smallest significance level at which it would reject the null hypothesis. If the value of the test statistic is f, then the corresponding p-value equals the probability that f, like the test statistic in general, is bigger than this particular value. This test statistic in general is the script f random variable, and that follows actually an f distribution with a q with parameters q and n minus k minus 1, or q n minus k minus 1 degrees of freedom. So you can actually calculate that. So what you need to do is to basically use the table and look up the actual value of the test statistic that you get. Let's look at an example. This example here is again taken from the book, and it's about Major League Baseball players' salaries. What you have here is, on the left-hand side, you have the log of salary, which is publicly known in the US, and on the right-hand side, you have performance indicators, for instance, the number of years this guy has been playing, etc. One might say that, well, performance really doesn't matter for salary, so one might be interested in, the performance related variables are here these three ones. Okay, and the test would therefore be that these three together have no impact, or each of them has no impact. So that means that beta 3 is equal to beta 4 is equal to beta 5 is equal to 0. Okay, so what we do is we run two regressions. One would be the full model. And the other one would be that you estimate this model leaving out these three variables. You get 2 times the sum of squared residuals. So for the restricted model, you get this sum here. For the unrestricted model, you get this sum here. I told you before that the unrestricted model can always better explain the data, right? The sum of squared residuals is always going to be lower for the unrestricted model. The question is how much, right? I have 353 observations, and I have 1, 2, 3, 4, 5, 6 degrees of freedom that I lose for the unrestricted model. So therefore, I'm going to have here this difference in the sums of squared residuals. So that's always going to be a positive number, as I said, divided by 3 restrictions, 1, 2, 3 variables that I'm basically restricting to be 0. And in the denominator, I have the sum of squared residuals for the unrestricted model divided by 353 minus 6, which is 347. So I'm getting a test statistic of 9.55. And when you go to that table of the F distribution, then you see that this is above the 1% critical value of 3.78. So the 3 performance variables are actually jointly statistically significant at conventional levels, right? And conventional levels are 1%, 5%, 10% sometimes. That's the conclusion of all this. The question now is, how can this actually be squared with insignificant t-stats for these variables? It could be that these 3 are jointly significant, but individually they're not. What is then going on? Well, it could be that the data does not really help you to tell apart which one of the 3 really has an impact. So what that would actually give you is relatively high standard errors for all of them, but it could still be that jointly they actually explain some of the variation. So they have a significant impact jointly. You just can't use the data to really tease apart where this is coming from. And one way to proceed then in practice would be to actually also estimate a model with only 2 of them in there, right? And then you can see which one makes the most sense. Final comment here. There's a special case, and that is interesting. So when you have one restriction for the Ftest, then you're actually getting a two-sided t-test in the end of the day, because a two-sided t-test is about testing one restriction, and the F statistic is actually just the squared t statistic. So that's the relationship between these two. Finally, again, for you in the PDF version of the slides, the 1% critical values for the F distribution, so that you can look up that number. So let me just go back one slide. So we had the 1% critical value 3.78, and what we had done is 3 and 347. So let's zoom in. 3. See, 4.31, 4.13. Go back. Sorry, 3.78. Here we are, 3.78, because we actually have to go all the way down. And as you can see here now, this starts above 120 degrees of freedom for the denominator. This ends our presentation here, my presentation here on inference. These are very standard tests that are discussed here. And again, this is all about quantifying how certain we are about our estimates of the parameter values, or put differently, how much we can actually learn from the data about these values. I hope you found this clear, and with this, all the best.